Welcome everyone. Thanks so much for tuning in. My name is Jan Franke. I'm one of the researchers on Amira's P1187. I've been asked to narrate a short presentation on the concept of the proposal. I understand that some people may not want to read a 37-page technical document. So before we get into P1187A, I thought I'd outline what we've achieved in P1187. The primary objectives of that project, which started 3 years ago, was to create a miniature hybrid EM and GPR sensor that spanned the frequency range from about 300 kilohertz up to about 30 megahertz. Now, the idea here was to improve penetration from a standard GPR system and also provide some electrical conductivity measurements potential from the dispersive part of the EM field. The idea was to make a sensor that was small enough that could be mounted on a drone or potentially within boreholes at a later date. So before we get into this, and I understand that there's going to be a variety of viewers, let's understand what GPR really is. It's a very simple concept. All we're doing is imparting a pulse of electromagnetic energy into the ground and listening for reflections. The things that reflect GPR energy are primarily three types of variations. Dielectric permittivity, which really is water content, electrical conductivity, and to a much lesser extent the magnetic properties of the ground. So how to create this, the electromagnetic field? Well, what we do is we dump a large amount of voltage, usually a couple hundred volts, into an electric field antenna, usually a dipole, and that creates a vibration in charge. Now, those moving charges, as we know from Maxwell, creates an electric field. Electric fields generate an orthogonal magnetic field, and so on and so on, and that EM field propagates outward. It propagates both into the air and as well as into the ground, which becomes important later. So what do we use GPR for in geophysics? Well, it's really not for mineral exploration at all. In fact, about 93% of GPR systems are used primarily for civil infrastructure applications, the most popular of which being finding pipes in the ground or pavement thickness or rebar in walls. Very high frequencies, these are usually 500 megahertz and higher, and very, very high resolution. In fact, GPR now is being used to detect cancer tumors in cancer patients at very high frequencies, but it's all ground penetrating radar. So that's very good, but not very useful for the mining industry. So we need to go much deeper. But there's a problem there. As we go deeper, maybe we use lower frequencies, there's some physics that come into play, and the first one being ohmic losses. So as the ground electrical conductivity increases, the GPR energy gets absorbed greater and greater. So we're ideally looking for an environment that is electrically resistive. The next problem occurs when we have high frequency energy that has very high resolution, short wavelengths, but we're encountering rocks, for example, in a tropical weathering environment, and each of those rocks cause scattering. And scattering, of course, disperses the energy each time it encounters a rock, and less energy is available to return back to the surface. Another issue is just geometric spreading. A GPR is not a laser, it is a flashlight, so the further down you go, the more and more energy is dispersed, and less of that is able to come back, directed back at the receiver on the surface. And as I mentioned before, the final problem is, as we get larger and larger antennas for lower frequencies, they can't be shielded anymore. We can't put a box around them or a Faraday cage. And what ends up happening is that their GPR energy bounces off everything, from grass blades to a person to a truck to a tree. So that creates all sorts of interference as well, and it becomes a very challenging obstacle in conductive environments. So this sort of graph, some of you may have seen these before, kind of outlines the most important things that we're looking for. So resistive environments, ideally open ground, so not in an urban environment. We don't want to be anywhere near saline groundwater. Ideally drier the better, and we're looking for more crystalline rock formations rather than fine-grained material, which again tends to be more conductive. So can we guess on how deep GPR can go? Yeah, we have a pretty good idea. We can model it reasonably well based on electrical conductivity. So what we see is, if we want any appreciable depth, let's say 40 meters or more, we need a conductivity in the range of about 4,000 ohm meters, which is, about 1,000 ohm meters, which is still pretty high. Well, how do we get deeper in a more realistic environment? Maybe 100 ohm meters. Well, can we increase transmitter power? Maybe. Can we increase our signal to noise ratio so we listen a little bit harder? Maybe. Or can we increase our signal to wavelength? We're already a very high resolution geophysics compared to other types of wave phenomena like seismic, where in the scale of meters on wavelength. So to go lower frequency and thus lower resolution may not be that bad. Well, let's look at increasing transmitting power. It doesn't actually work because to get an appreciable increase in penetration, it's a logarithmic scale. So now we need 100,000 volts, not just a couple hundred. And I don't think we want to be generating 100,000 volts into an RF system. That's a good way of destroying electronics or potentially killing someone. So that's not a great way to do it. Can we increase signal to noise ratio? Yeah, and we already do that. So using very, very fast analog to digital chips, we can sample that radar data that's coming back extremely quickly and sample it in 16,000 times more than we were able to do 10 years ago. So that dramatically increases the signal to noise ratio. Well, what if we could increase wavelength? That would give us some increase in penetration. So here's a quick graph that tells us that if we were, say, at about 30 megahertz, which is about the lowest that GPR goes these days in 100 ohm meters, we would get something in the range of 18 to 20 meters. But if you can get down to 8 megahertz, well, that would give you 45, maybe even 50 meters penetration, quite an increase. But there's a problem there. The problem is that these antennas then would need to be ginormous, 50, 60, 70 meters long. Could we shield them? Well, in theory we can. I've built the world's largest radar antenna, and that's on the right there. It's probably not the most realistic system to be using, though. So, what did P1187 do? We actually created a magnetic antenna. So instead of an electric field antenna in the E field, this is a B field antenna. And the nice thing about B field antennas is that they're not proportional in size to frequency. In fact, the longer a B field antenna is, the more sensitive it is. So what we were able to do is take a 6-meter long electric field antenna and condense that down into only 30 centimeters. In so doing, we were able to lower the frequency from about 30 megahertz being the lowest down to about 18 megahertz. And by doing that alone, we were able to increase penetration at some of the sites by about 75%. So that's great, but that's only the receiving antenna. So let's take a look at some of the data from a site in Western Australia. And this is essentially aeolian sand above a weathered surface and into a more homogeneous crystalline bedrock. And the exact nature of the geology is not as important as the comparison between the traditional GPR at the bottom and this new B field sensor at the top. So what we can see here is, whereas we used to get about 25 meters of realistic penetration, we're now seeing about 40 meters of penetration. So a significant increase, and we've already eliminated essentially half of the radar system. So a system that would have been 12 meters long is now only 6 meters long, plus a small antenna on a backpack. So that was phase 1. Phase 2, the objectives are to take it to the next step. We now need to create a magnetic field transmitter and a magnetic field antenna to emit that magnetic energy out and create an electromagnetic field. From there, we wanted to look at making a multi-static radar system. So that is a system where it would have multiple transmitters, multiple receivers, very much akin to traditional seismic reflection surveying. If we have antennas that are so small, perhaps we can mount them on UAVs or, more interestingly, in boreholes. So let's look at those applications. What would something like this look like? Well, it would simply be a backpack, and both the magnetic transmitter and receiver would be inside, maybe a small Pelican case with an RTK GPS antenna on top, which would be used obviously for positioning, but also for very accurate timing. And timing might be important because of doing this. Putting it on drones, for example, and that's very important. Now, you might say, well, so what? All we've created is low-frequency GPR that is smaller and lighter. Maybe we can put it on drones. That's interesting, but it doesn't really answer the needs of explorationists who are looking at deep undercover ore deposits. So why don't we look at now multi-static GPR? The concept of multi-static GPR has been around for ages. I mean, since the 1990s. and it dramatically increases resolution. Essentially, it can be used as a synthetic aperture acquisition system. We can pull out moisture information and, of course, derive EM conductivity measurements. Now, the problem has always been at 100 megahertz and above, the systems now are, you can buy them, they're hundreds and hundreds of thousands of dollars. They're used for agriculture, but they're incredibly bulky and, as I said, very expensive. Anything below 100 megahertz for more exploration activities, impossible due to size. I mean, these things would be the size of a house. So we could make a multi-static system and put it on drones, for example, or drag it behind a tractor for a number of applications. But there's one that's very interesting, and it's been touted around for the last 6 months since we've come up with this sort of concept of miniature low-frequency radar antennas, and that is looking at tailing storage facilities. TSFs are obviously of great concern these days. And what if we were to use a multi-static approach for radar in a permanent monitoring sort of situation? So everybody knows about radar tomography. It's the exact same thing as seismic tomography. You know, we're taking moving antennas up and down through boreholes. It's been done for probably 60 years now. And you get some very interesting data, very high resolution data, but what we get is a variation of radar velocities. From radar velocity, we can work out dielectric permittivity, and from dielectric permittivity, relative moisture content based on the top equation. Okay, well that's cool between two boreholes, but geez, you'd have to move and raise them and lower them. It's not very practical. But what if we mounted these things within the dams or on top of them or at strategic locations, and they were continually shooting between themselves? So in a sort of fashion that was automated, and it would create sort of an automatic radar tomogram between all combinations of ray paths. And you can do that from drill holes as well within the TSF. So have a series of ray paths that would create essentially a field that would be on 24/7 and monitoring changes. So it's change detection and water content. And of course, you'd need to model rain events or any other natural phenomenon, but it wouldn't take a lot of computational work to determine if there was something happening at a certain depth between two of these sensor modules. So what are the applications for a miniature low-frequency radar? Well, definitely an improvement in depth penetration. Pulling out that moisture information, possibly in conductivity, even if it's in the first 5 to 10 meters, might be important. And then putting them on drones and covering vast areas very rapidly is, of course, very attractive for certain exploration fields, particularly where vegetation cover does not need to be cleared or farm access does not need to be attained. And then, of course, monitoring for long-term moisture changes in TSFs. There's one other application that's kind of interesting. When you have a small antenna, remember we talked about that energy escaping upwards and bouncing off all sorts of things, creating a huge amount of interference. Well, may it be possible to have a shield around these antennas that would somewhat block some of that escaping energy? And that would have tremendous applications in places like the Pilbara, where so much of that data is lost because the energy going down is absorbed, so it's very, very faint compared to those strong reflections coming from the bench walls or from trees. So this is the outline for P1187. If you have any questions, please contact Olga. And I think you know how to reach Jim and myself if you have technical questions.